But actually, I had one more thing to say about DFAs before we move on. DFAs, come on now. DFAs cannot compute everything. Like, there are some languages actually that you cannot compute with a DFA. This is a fact that I've mentioned before, but I want to actually talk today about a specific example and try to explain why a DFA cannot compute any. Can I say DFAs can't compute every language? There are some languages. Another way of saying this is there are some languages which are not regular, right? Remember, a regular language is one which can be computed or can be accepted by a DFA, but there are actually some languages which are not regular. So I would like to do, let's just for today do one example of a non-regular language. We are going to talk in detail about non-regular languages in a few weeks, if this is interesting. But for now, I just want to do one example, just to demonstrate the fact that it is not easy to show that a given language is non-regular. You basically have to invent a proof sort of custom-made for the language that you're talking about. Unless you know some fancier tricks, which we will eventually get to, but I just wanted to do one sort of by hand. A non-regular language. Here is a language which is not regular. I'll tell you the example. It's not a very complicated language, but you cannot, this language cannot be accepted on any DFA. It is this. I'll call it L. A to the N, B to the N. Sorry, my pencil is acting up here, where N is a natural number. All right, this is, strings of A's and B's where it has the same number of A's and B's. This A to the N, B to the N, it's the same N. That's important. It's actually not hard to make a DFA which accepts A to the N, B to the M with two different exponents, possibly different exponents. We've done that, I think, on the homework or maybe on examples. This, though, turns out has no DFA can accept this language. So this, if I were to write the elements out, it includes the empty string. That would be when the exponent is 0. But it also has AB or A squared B squared or A cubed B cubed, etc. Right? This is the language I'm talking about. No DFA can accept this language. All right. So let's try and demonstrate that. No DFA can accept L. All right, I want to try to prove this. Now, the way you have to do this is basically by contradiction. We have to assume that there was some DFA which accepts L, and then demonstrate somehow that that's impossible. Right? You have to consider all possible DFAs in theory and show that none of them can possibly accept L. So let's do proof by contradiction. So I'm going to say, for a contradiction, assume that L is the language of some machine, some DFA, where M is, I'm going to write the M formally. You could think of M as a diagram, of course. You usually do think of M as a diagram, but actually when you're writing the proofs, it's usually the diagram is not helpful to phrase your language for the proof. Okay, so M is this DFA. And I'm going to try to show that this leads to a contradiction. All right. So here's the trick. This is not an easy proof to come up with, and part of why I want to go through this is just to demonstrate how tricky it is to show that something is not a regular language. You have to imagine any possible DFA and then somehow find a contradiction. Anyway, for this particular language, I would like to consider delta star of Q0 and A to the I for various I. I hope you can all hear me, by the way. I'm just talking in my kitchen here. Consider all things like this. So what this means is I'm going to just be thinking about, for various choices of that exponent I, where does the machine end up after you just do a bunch of A's? So it ends up somewhere after you do no A's. After you do just one A, where does it end up? After you do two A's, where does it end up? All right, this is what I want to consider. These are the states that it makes it to after reading a certain number of only A's, all right? Where this I, of course, could be anything, but the DFA, and this is a fundamental fact about DFAs, the DFA has only finitely many states. That means that this state, where the machine ends up after reading a certain number of A's, there has to be some kind of a repetition of these. As you increase the I could be 0, 1, 2, 3, anything up to infinity, but the number of states is only finite, which means there's some kind of repetition of states. When you just read A over and over again, it might go, think about going through a loop in the machine or something, but it has to come back at some point to a state that it's already visited. So I'm going to say, since there are finitely many states, these states for various I, they cannot all be different, because there's infinitely many different choices of I. So you cannot get infinitely many different states, because there are not infinitely many. There's only finitely many states. Since there are finitely many states, that means there exists, I'll say it this way, I and J with delta star of Q0 A to the I equals delta star of Q0 A to the J. And of course, I and J are different. All right. This means that there is at some point a state after you read a bunch of A's that actually is the same result as a state after you read some other bunch of A's. All right. Two different amounts of A's that you're reading, but they end up at the same state. This must occur because there are only finitely many states. All right. What that means is this means after I read I A's, I end up at the same place after I read J A's. But now check this out. That means that delta star of Q0 A to the I B to the I must be the same as delta star of Q0 A to the J B to the I. That's because the state you end up with after reading A to the I is the same as A to the J. And then if you follow that by B to the I both times, it has to still be the same because they started in the same place here, and then you did a bunch of B's. They're still going to be in the same place over here. All right? But the contradiction is that this is accepted. Let me say it this way. Oops. Oh no. Okay, this string here is accepted, but this string here is rejected. Remember, my language is defined to be the set of strings A to the N, B to the N, where the exponent is the same. So here the exponent here really is the same, and so this will be accepted, but the exponent here is different, which means that this is rejected. And that's the contradiction. I have these two states are equal. This equal sign means they are the same state, but on the one hand, that is an accepting state, and on the other hand, that is a rejecting state. All right, and that's a contradiction. So another way of saying this is that, well, can I just say this is a contradiction? I don't need another way of saying it. This is a contradiction. Since, apparently the same state, that equal sign up there means those are the same state, but on the one side it's accepting and the other side is rejecting. This is a contradiction since the same state can't be both accepting and rejecting. That's how we do it. All right. It's a weird little proof here, in my opinion, somewhat strange argument, and not also, in my opinion, not immediately obvious that this is how you should have done it. I began the little proof like this, which is not an obvious step, and in other languages which are not regular, you would do it a completely different way. This proof works for this particular example, but it is not a general purpose framework for showing that that languages in general are non-regular. This is why this is something that we're going to come back to later on, a more general purpose strategy for showing that languages are not regular. But I just wanted to do one example for now, just to convince you there really is such a thing as languages which are not regular. All right. Anybody got questions about that? I hope that this is clear. I mean, it should seem a little weird and technical, but I hope it makes sense at least. All right, great. Let's continue then. So there are some languages which cannot be accepted by a DFA. So let's talk about some other types of machines. As we go along, like I said, we're going to talk about different kinds of machines of increasing levels of complexity. So our next type of machine, new machine dropped, is called, this is very similar to the DFA. Other ones that we're going to talk about later on don't really look like DFAs much at all, but here's a new type of machine. This is called the NFA. It's very similar to a DFA. It has a few extra little tricks that it can do though. So N rather than D. NFA stands for non-deterministic. That's the difference. Remember, DFA means deterministic finite automaton. NFA means non-deterministic finite automaton. Non-deterministic is the big difference here. The non is what makes an NFA different from a DFA. So what exactly is the difference? It's still finite, which means we're still actually going to draw them with diagrams like the DFA, and it still is going to have finitely many states. That's what the finiteness means. The determinism bit is, I described this before about a DFA. What determinism means for a DFA is that the DFA always behaves the same for every input. So no matter what the input string is, if you do the same string every time, the machine will do the same thing every time. So every letter, the diagram tells exactly what to do if you see an A or a B from this position. All right. Non-deterministic means that the diagram kind of has the non-determinism here means that the NFA can produce several different results for the same input string. So in particular, this means that the NFA is allowed to have several outgoing arrows with the same label on it. The DFA, every state has, like one A arrow and one B arrow. But on an NFA, every state can have several different A arrows, which you imagine this is meaning somehow like the state, sometimes goes this way with an A and sometimes goes this other way. It's non-deterministic. That's what the non-determinism means. The NFA can produce several different results for the same input string. And you can think, sometimes people describe determinism versus non-determinism as being about like randomness. You can imagine the NFA is sort of a machine which it doesn't do the same thing every time. It might just like choose on its own, sort of at random, what to do sometimes. All right. Anyway, this is a little more highfalutin than it needs to be at this point. Let's just look at an example here, like so. Here is an example of NFA, which is not a DFA. All right. this is an example of NFA. At a glance, it looks the same as a DFA, but what's interesting about this one is that, for example, in the original state here, I have two different outgoing B arrows. It can go there, or it can go here, right? So here, if I were to give, could I give names to the two states here? In Q0, if we read B, we can go to Q1 or stay at Q0. This is illegal in a DFA. In a DFA, you're not allowed to have two arrows with the same label on one of the states. But in an NFA, it is legal. It means, it means when you're in this state, if you read a B, you could go over here, or you could stay in this state. That's how NFA looks. All right. Now you might wonder, what does it even mean for a string to be accepted then if you could go different ways with that string? Like for certain strings, there are some trails which might be accepted and some other trails which might be rejected. What it means to be accepted is that one possible trail in the diagram leads to an accepted state. If that's true, you say the string is accepted, even if there are other sort of dead-end trails that don't lead to accepting states. So we say, I'm going to write that down. We say a string is accepted by NFA if any of the possible final states is accepted. All right. If any of the possible, for a given string in an NFA, there are many different ways that you could run it through the diagram. And this is what makes NFAs slightly more complicated, I suppose, to tell if a string is accepted or not, because you really need to consider all possible trips through the diagram following that string. It's called accepted if any of the possible final states is accepting. So, for example, in this, in the diagram that you can see on the top of the page here, can somebody tell me a string which would be accepted here? Somebody want to shout it out?
B.
B, yes, thank you. That's the simplest accepted string in this example. To get from here to here, you can do B. So B is accepted. Can someone else give me another one? Perhaps a little more interesting? No offense to Joe.
BB.
All right. Yes, thank you. BB is also accepted. You could go B and then B. That would be accepted. All right. B is accepted. Also BB, very enthusiastically. All right. BB is interesting because you could also, actually this is true of B also, you could have done BB and it's just stay over here the whole time, and then you're not in an accepting state. But that doesn't mean that it's rejected. It just means that that particular way of doing it was rejected. There is another way of doing it which is accepted. So BB is also accepted. Can someone tell me a string which is rejected on this machine?
A.
Yeah, somebody said A. A is rejected. That's because if you start here and you do A, the only way to do that is right there, and that's rejected. So A is rejected. Something else that's rejected would be AB, right? Because the only way to do AB, sorry, not A, I meant BA. BA is also rejected. Because the only way to do BA would be starting here. Actually, there are a few ways to do it. You could go across and then back. That's one way to do BA. Or you could actually do BA by staying here both times. BA, do the loop twice. But anyway, either of those two ways, you end up in the rejecting state. There is no way to do BA and end up in the accepting state. All right. This is, so the question of is it accepted or not is more complicated on an NFA. On a DFA, it's always very cut and dry. You just follow the arrows one at a time. On an NFA, you have to actually consider many different paths sometimes. And sometimes it can be really very difficult to decide. All right. Great. So BA is rejected also. I should have finished writing that. Also rejected. Okay, great. This is NFA. An NFA, I'll give you another example. An NFA can have any number of outgoing arrows of each letter. Right? In that example, there were, like here, there's 2 outgoing B's from this state. There's one there and one there. That's what made that non-deterministic. But actually, it can have any number of outgoing arrows of each letter. Just for emphasis, I will say even zero outgoing arrows of a letter is allowed. So, for example, and actually most of the NFAs that we use are going to be of this type. So if it seems like on one level NFAs are more confusing because there's just so many different paths that you could take, but some NFAs, depending on how you make it, are actually very clear. So here's an example of an NFA which is very clear in my opinion. That's an NFA. I said it can have any number of outgoing arrows of each letter. So from the first state, there's one outgoing A, it's this loopy one. There's 2 outgoing B's, there's the loop and this one. And then from this state, there are no outgoing letters at all. All right. And so can we ask, actually in this case, it's very, this is a very nice DFA in my opinion, because it's very clear to me what kinds of strings are accepted on this NFA. Did I say DFA? I meant NFA. This is a very nice NFA. What kinds of strings are accepted here? Well, when I look at this NFA diagram, I say, okay, I'm going to start here. And then if I want to, I can do this loop forever. So at the beginning of the string, at least, you can do whatever you want. But if you want to be accepted, you have to finish with a B and then stop. You can't do anything else because there are no arrows after that B. All right. So actually this here, this accepts any string ending with B. All right. Because on the diagram, I can see very clearly you do whatever you want here for as long as you like. But if you want to make it to the accepting state, you have to finish with a B and then not do anything else, because you're not allowed to do anything else after that B. All right, this accepts any string ending with a B. This is, in my opinion, a little nicer than there is also. You can also make a DFA which accepts any string ending with a B, but this to me is a little clearer. The structure.
Does this read more than one letter at a time then? Because you don't have an arrow going back for A. So how do you know it ends with a B? Or does it read and see that there's nothing after the B?
So when a string is accepted means you read through the whole string and you end up in the accepting state.
Yeah, I was just wondering how it would do how it would like figure out which B path to follow.
Yeah, the answer is it doesn't really figure out. Like, for example, I can say, you know, A, B, A, B is accepted, whereas A, B, A is rejected. When I say that, what I mean is this string, so to say it is accepted, it means there is a path through the diagram reading these letters which ends in the accepting state. And the way to do it is I go A, B, A, B, and I end in the accepting state. Now, you might ask, well, how did you know to go across at the last B and not to go across at the second B? And my answer is, I just know. I mean, how does the machine know? The machine doesn't really know anything. It's just when I say this string is accepted, what that means is there is some way to read all these letters one at a time and end at the accepting state. How to determine, imagine yourself as the machine, how do I figure out which way to do that is another question that really is not something that we're gonna think about too much. I hope that answers the question. It's weird because at DFA it is always obvious how you're supposed to read the arrows from step to step because there's only one choice. And similarly, this is rejected. What that means is there is no way to end up over here after reading all of these letters, because how could you read all of these letters? You could go A, B, A, A. Actually, that's the only way you can read all of these letters on the diagram. If you go across with this B, you could go A, B, then you're stuck and you're never going to get to the end of the string, and so that counts as rejected. It's a little weird, but this is how the NFA works. Any other questions about that? This takes a bit of getting used to, but we can handle it. All right. How about this? I got another example. This is a similar example. I'm just going to try and draw. It's almost the same picture, but kind of the other way around, perhaps. All right. Ooh, here's an NFA like this. Anybody want to say? Can you say what strings are accepted on this NFA? The question is something like, what does it actually take to end up in this state after reading a string? I heard something. I think it was a mistake.
Would it be any string starts with the letter B?
Yeah, any string starting with B, she said. This accepts any string starting with B. What you want to think about is, what are the strings which could possibly end up over here? And the answer is, if you want to start here, which you do, you must do B first. But then after that, you can do whatever you want, because you can do any A's and B's after that. So this one accepts any string starting with B. Right? Another way of writing that is, if you prefer, BX, where X is in AB star. Remember, this means X in AB star means that can be any string. B, but it has to start with B. B first, and then whatever you want afterwards. All right? It's a little confusing, but actually, in my opinion, I don't know if you will grow into this feeling. I actually kind of like NFAs a little better than DFAs. To me, it is easier to make a NFA for a language than it is to make a DFA, because actually this, when I write it this way, BX, where X can be anything, this more or less directly translates to this diagram in my mind. Once you get used to this, I'm not trying to flex on you. Once you get used to making NFAs, I think you will find it's actually a little bit easier than DFAs. You can make a DFA for this language, but it's a little more complicated. I think you need 3 states, and you need to. It's more complicated. At least in my mind, I have an easier time thinking about things in terms of NFAs than DFAs. All right. How about, let's just try one more example. How about an NFA? I got some for you to try too, but here I'm going to describe the language and try to make an NFA. An NFA for strings with the second to last letter of A. All right. Where the second to last letter is A. I'm going to try to be inspired by this one here. This one is where the last letter is B. Come on now. This one, right? That says the last letter is B. The way I think about this is I could do anything, 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 but then I have to finish with a B and stop, right? So I'm going to try to do something like that. Second to last letter is a A. That means I could do anything, anything, anything at the beginning, and then an A, and then one more thing, and then stop. So the way that I would write that is, here's my anything at the beginning. You can do whatever you want for as long as you like at the beginning of the string. And then, sorry, I'm under my face there. And then I do an A. And then one more thing, and then stop. The one more thing could be an A or a B. So I'm going to be like this. And then it's accepted. This is an NFA for strings with second to last letter being A, all right? So the way that I sort of visualize this machine is, ooh, something's messed up with my pencil here. This is like anything, a single A, and then over here, one more letter, right? Maybe these should be pointing at the arrows. I don't know. It's however you want to think about it. Maybe that's a little better. All right. This is an NFA which accepts strings where the second to last letter is a A. You can also make a DFA for this language, but it's a lot more complicated than that. It involves, well, it's more complicated. This is, to me, NFA is the more natural way of making this language than the DFA. All right, I got some for you all to try here, and I'm sorry that I can't, walk around the room and inspect and infect you, but I have 3 examples here. Maybe we can just try for a few moments. Oops. Come on now. Let's try make an NFA to accept these languages. I got 3 of them. How about AB, sorry about my pencil here, ABXA, where X is in AB star. So that means it starts with an A and then a B and then has whatever and then ends with an A, right? How about XB such that X has an even number of A's. So this one, the X part has an even number of A's and then it ends with a B, and that's accepted. My hint for that one would be think about the even odd sort of DFAs that we've done in the past. Do something like that, but then also say it has to end with a B. And then the last one. This one's a little weird. This is any string on A and B squared. That means that the string can use A's and B's, but the B's have to be together in blocks of 2. So this is like, A, B squared, A, B squared, A, or A squared, B squared, that counts. As long as the B's are together in blocks of 2, or B to the 6, that counts, but not something like BAB, because those B's are not in blocks of 2. All right, see what you think. I will, I suppose I won't do anything while you try them out. I'll wait, I'll give you 5 minutes or so to try them out. And then we'll talk about them, maybe a little more than 5 minutes. I will get myself a beverage. I'll give you a few more minutes. If you got questions, feel free to put them in the chat. I'm good for it. Hit me up in my DMs. Let's take one more minute and then we'll chat about them. All right, your 1 minute is up. Can we talk about them? Because we gotta go soon. ABXA, where X is an AB star. This one is similar to ones that we did above. This means that it starts with an A, then a B, then does whatever, and then has an A at the end. You can do this in 4 states. I would say first you must do A, so it's like that. Next, you must do B, so it's like that. Next, you can do anything you like. So at this state, I'm going to put a loop with A comma B on it. That means I can do, oh man, my pencil is getting worse. I have spare tips, but I keep them in my office at school. Maybe I should have come in today. All right, like so. So far, there's only one sort of way that you can progress through the diagram, and it must be starting with A, followed by B, then anything you like, and then one last A, and it should be accepted. So is just like that. That's my NFA. I hope that's what you came up with. This is an example, in my opinion, where the NFA is very clear, just basically a translation of this set theory description. Anybody come up with that? I hope so. Anybody have any questions about that one? This I intended to be the easy one. The other two are a little more complicated, more interesting. All right. I hope you got that one. Okay. Next was XB, such that X has an even number of A's. Right. Anybody work this one out? I know it's hard to describe in words. If I were walking around, I would look at your paper and say, great job. Or, no, that's terrible. I wouldn't say that. An even number of A's. I would, so it has to have an even number of A's, but then finish with a B, all right? So what I would first do is think about the machine just to do the even number of A's part as a DFA. We've done that several times before. That would look like this. It's this kind of back and forth thing with A's, right? But it could have any number of B's. This by itself is a DFA for even versus odd number of A's. Now, one thing that you will immediately realize if you think about it a little bit, every DFA automatically is a NFA, right? Every DFA counts as a NFA. This is a DFA, but I could also interpret it as a NFA, which just happens to have only one arrow outgoing for every letter. Did anybody, starting with this, there's actually a simple modification you can make here, or you can change the diagram a little bit to make it accept this. I want even number of A's, but then finish with a B. Did anybody work this out? Can describe how to change this?
I put a third state going from the starting state.
Yeah.
And I made that the accepting state, and it gets a B.
Yeah. Like this. I hope that's what everybody else did and is not saying it. Yeah, this one. So why did it go from here? It's because this is the state which represents even numbers of A's. You have to do an even number of A's to get back here. And then you finish with a B. That's how it goes. Yeah, this is exactly how I would have done it. I hope that you did it that way too. All right. And then the last one, we just got a couple more minutes. That's enough time to talk about the last one, which was AB squared star. This means every string made up of A's together with B squareds. So another way of saying this is it's any string at all, but the B's have to come in blocks of 2 each. Every time you see a B, there needs to be another B right after it. You're not allowed to have just a B, a single B all by itself. It has to be 2 B's at a time. The way that I would think that through is something like, I can start off, you can always do as many A's as you like. So this is the way that I would begin. You cannot also do whatever B's you like because B's have to come 2 at a time. Now, you might be tempted to just say, can I just do like this? You can't do that. On a NFA or a DFA, every arrow must be labeled with a single letter. You can't label an arrow with a string. It has to be a single letter. So you cannot do that. You need to make it so that the B's have to come one after another. Every B needs to have one more B after it, not another A. Did anybody work this one out? Any ideas? This one's a little tricky. I don't know if you didn't figure it out or just don't want to say it, but we got to go anyway in a moment. So I'm going to tell you, I did it like this. If you see a B, you must have another B also right afterwards. And then I make this the accepting state. Come on, like that. So this says over here you can do as many A's as you like. You can also do B's, but every time you do a B, you must immediately do another B. You can't do anything else in between these two B's. That's why there's no other arrows on this state over here. Anyway, that's this language, A followed by B squared with the star. All right. And I think that's about all I wanted to do today. So this was our first baby steps with NFAs. We're going to be talking about NFAs quite a bit more next time and next week also. All right. Thank you again for your patience doing the Zoom thing. Hopefully this will be the last of it, and I look forward to seeing you all on Friday.